Hello, my name is Matthew Abate, and today I'm going to be speaking to you about some of the work that myself and my collaborator Max Dutrex have been conducting in the Georgia Tech Facts Lab and the Georgia Tech Decision and Controls Lab. The title of my presentation today is Tight Decomposition Functions for Continuous-Time Mixed-Monotone Systems with Disturbances, and this work was advised by Dr. Sam Coogan. A system is mixed monotone when there exists a related decomposition function which separates the system dynamics into increasing and decreasing components. And this decomposition function is useful for, amongst other things, efficiently computing reachable sets and forward invariant and attractive sets for your original system. However, a main challenge in this approach is just identifying a suitable decomposition function for one setting. There are certain special cases and algorithms for when a decomposition function can be computed readily directly from the system dynamics. However, until recently, the question of existence of decomposition functions had never been explored. And while we study continuous time systems in this work, the question of the existence of decomposition functions was recently studied in the discrete time setting by Yang and Oze. I'm including a reference at the bottom of the slide where it was shown that all discrete time systems under certain assumptions are mixed monotone, and that a decomposition function for these systems can be computed using an optimization problem. So in this work, we study an analogous question in the continuous time domain, and we similarly show that all continuous time systems under certain assumptions are mixed monotone, and that a decomposition function can be computed by solving an optimization problem. Moreover, this decomposition function is tight in the sense that when used with the standard tools for mixed monotone systems, it will produce the tightest possible approximations of reachable sets that the theory allows for. And I should note also that while our decomposition function, our tight decomposition function, is also similarly expressed in terms of an optimization problem, we show through several examples in this work how in certain instances tight decomposition functions can be computed in closed form. So in this work we consider systems x dot is equal to f of x and w as in equation 1, where x is the state and w is the disturbance input. And we assume that the space of disturbance inputs is a hyperrectangle. Additionally, we denote by equation 2 the time t reachable set of the initial system from some given set of states x naught. So this is the set of states which are reachable at time t from x naught under any given disturbance policy satisfying that w is in the disturbance set for all time. Next, I'll present the definition of mixed monotonicity for continuous time systems. So the system x dot is equal to f of x and w is mixed monotone when there exists a related decomposition function which separates the system dynamics into increasing and decreasing components. As stated previously, there do exist certain special cases and algorithms for generating decomposition functions in particular instances. However, until now it has not been known whether or not all systems as in x dot is equal to f of x and w are mixed monotone. So when a system is mixed monotone with respect to D, the decomposition function is applied through the use of a deterministic auxiliary embedding system. Here this embedding system is given as equation 3. So it's important to note here that the embedding system is deterministic in the sense that it has no disturbances, and it's also monotone with respect to a particular order. Okay, and the fact that the embedding system is constructed from the decomposition function ties this monotone system to the original dynamics, and it can be used to show certain properties of your initial system. So in particular, I've included a proposition at the bottom of the slide where we show how finite time reachable sets for the initial system are efficiently over-approximated using a single trajectory of the embedding system. So the idea here is your initial system is non-deterministic, it's got disturbances, it might have some initial set and you might not know where it's going, but if you can conduct one simulation of the embedding system which has no disturbances, then a hyperrectangular set in your initial system state space can be constructed from that trajectory of the embedding system, and this hyperrectangular set is known to bound your reachable set. So this is an efficient algorithm for over-approximating reachable sets. So there are three main contributions of our work. First, we answer the question of existence of decomposition functions, and we show that any continuous time system possessing a vector field that is Lipschitz continuous in state and disturbance will admit a continuous time decomposition function. This decomposition function is constructed as an optimization problem. However, we show through example how a closed form decomposition function can be computed in certain instances. Additionally, we provide a notion of tightness in the procedure. So when a system is mixed monotone, it will generally be mixed monotone with respect to multiple different decomposition functions. However, until now, it has not been known whether or not there is some way of assessing the decomposition functions against one another and determining which is preferable to use in application or which provides the tightest approximation of reachable sets when used with the tools of mixed monotonicity. And our last contribution is to show how under-approximations of reachable sets are also computed using the tools of mixed monotonicity by considering the backward time dynamics of one system. So this is a useful contribution because up until now the tools of mixed monotonicity have only ever been applied to compute, say, over-approximations of forward time reachable sets or over-approximations of backward time reachable sets. I'll begin by addressing our first two contributions. So we'll define a notion of tightness and say that a tight decomposition function for our system is a decomposition function delta, such that for any other decomposition function d for the system, the constraints given as equation 5 hold. And we show through the proposition provided on the bottom of this slide how this definition of a tight decomposition function resolves a notion of tightness for mixed monotonicity. And in particular, if you compute an over-approximation of a reachable set using a tight decomposition function, that approximation will be contained inside any other approximation derived using the tools of mixed monotonicity. So a tight decomposition function will always provide the tightest possible reachable set approximation attainable. On this slide, we present our main result and show that all systems as an x dot is equal to f of x and w with the Lipschitz continuous vector field will be mixed monotone with a tight decomposition function defined element-wise by the optimization problem 7. So the intuition here is that 7 will provide either the minimum or maximum evaluation of the vector field f over a hyperrectangle. And this not only ensures that the system x dot is equal to f of x and w is mixed monotone with respect to delta, but it also ensures that any other decomposition function for the system will provide a less tight approximation of reachable sets when used with the tools of mixed monotonicity and the propositions provided on the previous slides. While the tight decomposition function construction in our work is presented as an optimization problem, we show through example, in particular the example on this slide, how in certain instances a closed-form tight decomposition function for the system can be computed. So in this case, we consider the system 8, and we show that this system has a closed-form tight decomposition function given by 9. Next, we'll show how under-approximations of reachable sets are similarly computed using the mixed monotonicity property, and this procedure uses the backward time dynamics of the system. So we say that the system x dot is equal to f of x and w has backward time dynamics given by equation 10, where again x is the state and where the disturbance is still contained in the same disturbance bound as the forward time case. So now in the case that the backward time dynamics are mixed monotone with respect to some decomposition function, a similar system, given here as equation 11, can be constructed such that trajectories of this system can be used to compute under approximations of reachable sets for the initial forward time system. And there's a notion of tightness here as well, so that when you have a tight decomposition function for the backward time system, with this theorem it can be used to produce the largest possible under approximations of forward time reachable sets. The procedure presented on the previous slide requires a decomposition function for the backward time dynamics, and in general, decomposition functions for the backward time dynamics can be computed using the same methods that you would in the forward time case. However, here we're going to present a special case for when a tight decomposition function for the backward time dynamics is computable readily from a tight decomposition function from the forward time dynamics. And in particular, when fi does not depend on the ith variable in x, then you can just form a tight decomposition function for the backward time dynamics by flipping its inputs and negating the sign. So I'll next present a numerical example to demonstrate the theory and tools in our work. We'll consider the three-dimensional polynomial system given by equation 13, and where the disturbance bound in this case is a hyperrectangle. Okay, so this system is mixed monotone with a tight decomposition function computed in closed form using equations 14 and 15. And on the following slides, we'll show how this decomposition function facilitates the approximation of reachable sets for the system. So we'll take an initial set, here shown in red, which is a cube in R3 centered at the origin, and we'll aim to predict the time 1/2 reachable set of this system. The true reachable set of the system is shown in green, which was computed using an exhaustive simulation, and a hyperrectangular over-approximation of this reachable set was computed using the tight decomposition function and is shown in blue. And on this slide, we're going to project the previous figure onto the x1, x2 planes. So we're projecting it to R2. And again, the initial set is shown in red. Here it's a red square. The time 1/2 reachable set is shown in green. and the over-approximation of our reachable set, which is computed using the tight decomposition function, is shown in blue. So we see here in the projection that the blue approximation is actually a reasonably good approximation of the true time 1/2 reachable set of our system. And additionally, we're going to apply the special case and also the theorem that we've introduced to compute a tight decomposition function for the backward time dynamics, and then also compute an under-approximation of the time t reachable set of our system in this manner. So this under-approximation is shown in pink in this figure. All right, thank you for listening. I'll just wrap up now by mentioning our conclusions and contributions. So in this work, we show that all continuous time systems possessing a vector field that are Lipschitz continuous in the state and disturbance emit a Lipschitz continuous decomposition function, and additionally, we provide a notion of tightness and a construction for the decomposition function that provides the tightest possible reachable set approximations using the mixed monotonicity property. While this decomposition function is provided as an optimization problem, we show through a few examples how in certain instances this tight decomposition function can be computed in closed form. And also we present a method for under-approximating reachable sets for mixed monotone systems, and this procedure uses the backward time dynamics. Thank you for listening. My name is Matthew Abate, and I've included my contact information at the bottom of this slide.